Hi girls, let's continue with question 4. In question 4, we will identify the phenomena associated with electromagnetic induction, which fulfills Lenz's law and confirms that there is no ideal physical quantity. Eddy currents are currents generated in any piece of metal moving through a magnetic field. The magnetic field that opposes the motion that caused the currents. So here you can see that when we approach the magnet, the number of magnetic field lines penetrating this piece of metal increases. Once it increases, we have a change in the magnetic field, and this piece of metal generates a current that generates an induced magnetic field in the opposite direction of the original one to try to decrease the original magnetic field. These currents look like vortexes, the WAMAT. This is why they are called eddy currents. And you can see that the direction of the eddy currents reverses when we remove the magnet or pull it away from the piece of metal. That's because when we pull the magnet away, the number of magnetic field lines penetrating this piece of metal decreases. Thus, a current will be induced in the piece of metal that generates another magnetic field that tries to increase the original magnetic field again by being in the same direction. Again, these currents are called eddy currents because they are formed or forming continuous loops on the surface of the piece of metal. Eddy currents are used to create braking effect in metals in a process known as the eddy current damping. So you can see here that eddy currents are used to slow down trains or roller coasters and sensitive balances. In this sensitive balance, the other side, we have a magnet and a piece of metal. When you put a gold bar or a gold nugget on this plate, it starts to vibrate up and down. When it starts to vibrate up and down, this piece of metal starts moving up and down as well. Due to relative motion between this piece of metal and the magnetic field, a current will be induced in this piece of metal that always opposes the change in the original magnetic field. When it's moving away, the original magnetic field is decreasing. So it will create a current that induces a magnetic field that tries to increase it back up. And when it goes back down, the magnetic field penetrating this piece of metal increases. So it will induce a current that creates a magnetic field opposite to it to try to decrease it again. So what happens is that this piece of metal balances between the north and south pole, preventing this plate from jumping up and down. So it will give you a correct measurement for the amount of gold. Now, not always that eddy currents are good. Eddy currents in a motor heats the motor core, which is a disadvantage of eddy currents. To reduce the eddy currents, the core is laminated. That means that it is sliced into thin pieces, and you have an insulation between each piece and the other. When that is done, it increases the resistance of the iron core of the motor. When you increase the resistance of the iron core, the amount of the eddy currents decreases according to Ohm's law, and hence we have decreased the eddy currents forming in the motor core, and we decreased the power losses in the motor core as well. Question 2 and question 11 relate the turn ratio. 1 minute, let me just try to fix the timing on the slides. All right, so relate the turns ratio of a transformer to its corresponding voltage ratio and apply the corresponding equation in problem solving. 2. Apply the ideal transformer equation to solve numerical problems. 3. Differentiate between the step-up and step-down transformers. And question 11 says, explain how transformers are used in the national grid system to transmit power through long distances with minimal power losses. Now, a transformer is a device that is used to increase or decrease the source voltage with relatively little waste of energy. And you can see a live transformer here. We have two coils and a metal core here, or an iron core. One of the coils would be connected to the source of voltage, like the generator or any source of AC voltage, and the other coil is connected to a device like houses or any electrical devices that need power. These are the transformer parts. We have an iron core is used to trap the magnetic field produced by the wires and increase it. We have the primary coil, which is the coil connected to the source of the voltage. And on the other side, we have a secondary coil, which is the coil connected to the load, the electrical device, like a refrigerator, like a light bulb, any kind of device that requires electricity to work. Let's watch this video now to learn about transformers.
The relationship between power, voltage and current is vital to the way electricity is supplied to our homes. The higher the current or voltage, the more power is available. When electricity was first produced commercially in the late 19th century, the current flowed in a single direction. This is called direct current, or DC. To produce more power with DC, higher currents were used. But passing higher currents along power lines resulted in huge power loss through heat, making it impossible to transport electrical power over long distances. An ingenious solution had to be found. If the flow of electricity switches direction back and forth, we call this alternating current, or AC. As it does this, the voltage is changing as well. This unique property of AC has allowed engineers to develop a way of increasing or stepping up the voltage in power lines. Now the current can actually be decreased while maintaining the same power, and so AC electricity can travel long distances without any significant power loss. The voltage in power lines is changed using transformers. In essence, a transformer is simply a metal core surrounded by two coils of wire. The first wire will only be coiled a few times. The second wire will be coiled many more times. The changing voltage in the first coil creates a changing magnetic field, which induces a voltage in the second coil. The voltage induced in the second coil is greater, as the coil has more turns. Because the power must remain constant and the voltage is increased, the current must decrease. National grids around the world step the voltage up to around 400,000 volts to transport low-current electricity over vast distances with minimal power loss. But this electricity is useless in your home. The voltage is dangerously high, and the current is too low. To make this electricity useful, it is put through another transformer, this time the other way around. Step-down transformers step the electricity back down to a sensible, low voltage, along with a useful high current. And so transformers are vital to manipulate voltage in power lines and convert high voltage AC electricity to be safely used in your home.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at how transformers work. Now this follows on from our series on electrical engineering, so do check out the other videos if you've not done so already. Links are in the video description below. Coming up, we'll be looking at how to create a magnetic field with electricity, why only an alternating current can be used in transformers, how a basic transformer works, then we'll look at step up and step down transformers, and finally we'll finish on three-phase transformers. Now there are two types of electricity, AC and DC, but transformers can only work using AC or alternating current. Now if you don't know the difference between these two, then please first of all watch the video on electricity basics first. Again, you can find links to these videos and other useful videos in the video description below. When we connect an AC generator to a closed loop of cable, a current will be able to flow through this cable and the direction of the current will alternate backwards and forwards with the rotation of the generator. The alternation means that the current reaches its maximum and minimum point during the cycle, which gives it its sine wave pattern when connected to an oscilloscope. Now you can think of this as the tide of the sea as it changes direction and reaches its maximum and minimum point. As the current flows through the cable, it will emit a magnetic field. If we pass DC current through the cable, the magnetic field will remain constant. But if we pass AC current through the cable, then the magnetic field will increase and decrease in strength and changes polarity as the current changes direction. If we place multiple cables together and pass current through them, then the magnetic fields will combine to create a stronger magnetic field. If we then wrap the cable into a coil, the magnetic field will become even stronger. If we then place a second coil in close proximity to the first coil and then we pass AC alternating current through the first coil, then the magnetic field it creates will induce a current into the second coil, and this magnetic force will push and pull on the free electrons, forcing them to move. The key component here is that the magnetic field is changing polarity as well as intensity. This change in intensity and direction of the magnetic field constantly disturbs the free electrons in the secondary coil, and this forces them to move. This movement is known as electromotive force, or EMF. Electromotive force does not occur when we pass DC current through the primary coil, and that's because the magnetic field is constant, so the electrons are not being forced to move. The only time it will cause EMF is very briefly when the primary circuit is opened and closed, or when the voltage is increased or decreased, and that's because these actions result in a change to the magnetic field. Therefore, we use alternating current as this change occurs constantly. Now the problem with this setup is that a lot of the magnetic field from the primary side is being wasted because it's not in range of the secondary coil. So to fix this, engineers place a core of ferromagnetic material such as iron in a loop between the primary and secondary coils. Now this loop guides the magnetic field along a path to the secondary coil so that they will share the magnetic field, and this makes the transformer much more efficient. Now the use of an iron core is not a perfect solution. Some energy will be lost through something known as eddy currents, where the current swirls around the core and this heats up the transformer. And this means that the energy is lost as heat. To reduce this, engineers use laminated sheets of iron to form the core, and this greatly reduces the eddy currents. Transformers are manufactured to be step up or step down transformers, and these are used to increase or decrease the voltage simply by using a different number of turns within the coil on the secondary side. In a step up transformer, the voltage is increased in the secondary coil, and this will mean that the current will decrease. But don't worry too much right now about why that occurs. We'll look at this in a later electrical engineering video. To increase the voltage in a step up transformer, we just need to add more turns to the coil on the secondary side than the primary side. In a step down transformer, the voltage is decreased in the secondary coil, which means that the current increases. To do this, we just use less turns in the coil on the secondary side compared to the primary side. For example, a power station needs to transport the electricity it has generated over to a city some distance away. The power station will use a step-up transformer to increase the voltage and reduce the current, as this will reduce the losses through the long transmission cables. Then, once it reaches the city, this will need to be reduced to make it safe and usable by buildings and homes, so there will need to be a step-down transformer. The transformers for commercial buildings and power stations are usually in a three-phase configuration. You'll see these placed around your cities and towns, and they'll look something like this. These three-phase transformers can be made from either three separate transformers that are wired together, or they can be built into one large unit with a shared iron core. In this setup, the coils will typically sit concentrically within one another, with the higher voltage coil on the outside and the lower voltage coil sitting on the inside. Now these coils are insulated from one another so that only the magnetic field will pass between the two coils. To connect the two sides, there are many different configurations, but one of the most commonly used is to connect the coils in a configuration known as delta Y, sometimes referred to as delta star. This refers to the primary side being wired in a delta configuration and the secondary side being wired in a Y configuration. The center point of the Y side, where all three connectors meet, is often grounded, which allows for a neutral line to also be connected. We'll cover transformer connections and calculations in other more advanced videos, as this can get quite complex. So for now, simply focus on how they work to build your base knowledge. Okay, that's it for this video. Thank you very much for watching. I hope you've enjoyed this and it has helped you. If so, then please don't forget to like, subscribe and share this video. You can also follow us on Facebook, Instagram, Twitter and Google+, as well as our website, theengineeringmindset.com.
So as mentioned in the video, the working principle of a transformer is as follows. When the primary coil is connected to an AC source, we will have a changing current flowing through the primary coil. And since we have a changing current, it will create a changing magnetic field around it. This changing magnetic field changes in both the magnitude and direction with the changing direction and magnitude of the current. This magnetic field would be trapped in the iron core. It will all be accumulated and gathered in the iron core. This magnetic field, this changing magnetic field produced by the primary coil will affect the secondary coil, and it will induce a current in it. Because we have a changing magnetic field, we will have an induced current in the secondary coil. So when the primary coil is connected to an AC source, the changing current creates a changing magnetic field that is carried through the core to the other coil. In the secondary coil, the changing magnetic field will induce a varying EMF and current. An EMF and current in one coil due to the changing current in another coil is called the mutual inductance. So here we have a mutual inductance between the two coils, the primary and the secondary. We have two types of transformers. We have a step-up transformer that is used to step up the voltage, and we have a step-down transformer that is used to reduce or step down the voltage. In a step-up transformer, the number of turns on the primary coil is less than the number of turns on the secondary coil. You can see that it creates some kind of a portal where the voltage comes from here, from the primary coil, gets magnified and becomes bigger from the secondary coil. So the number of turns on the primary is less than that from the secondary. As a result, the voltage on the primary coil is less than the voltage on the secondary coil. As we said, this is a step-up transformer. That means that the voltage on the primary coil would be less than that of the voltage on the secondary coil. It increases the voltage. That means that Vs is bigger than Vp. But to maintain the same amount of power according to the law of energy conservation, if we step up the voltage, the current is reduced. That means that the secondary current would be less than that of the primary current. So IP, you can see here IP is 10 and IS is 2.5. For a step-down transformer, you can see that the opposite happens. The number of turns on the primary coil is bigger than the number of turns of the secondary coil. The voltage gets minimized. So the voltage on the primary coil would be bigger than that on the secondary coil. So Vp is bigger than Vs. As a result, the current will happen, or the opposite will happen to the current. That means that the current on the secondary coil would be bigger than the current on the primary coil. So Ip is less than Is. In both types of transformers, the power is constant. That means that the power on the primary coil is equal to the power on the secondary coil. Now remember that the power is the multiplication of the current and voltage. So if I want to find the primary power, or the power on the primary coil, I will multiply the primary current times the primary voltage. 10 times 100 is 1000 watts. If I want to find the power on the secondary coil, I will multiply Is times Vs. The secondary current, 2.5, times the secondary voltage, 400, gives you also 1000 watt. Similarly here, if you multiply 2 times 1000, that gives you 2000. And if you multiply 200 times 10, that's going to give you 2000 as well. So the primary on, or the power on the primary coil is equal to the power on the secondary coil. An ideal transformer changes the voltage with no power losses. So the power on the primary coil is equal to the power on the secondary coil. We can substitute each one's equation and get this new equation. So Ip Vp equals to Is Vs. If you try to connect the equation with the number of turns, you'll see that Vp divided over Vs, the primary voltage over the secondary voltage, is equal to the number of turns on the primary coil divided by the number of turns on the secondary coil. Let's solve a question. A step-up transformer has a primary coil consisting of 200 turns. So this is how many turns we have on the primary coil. So this coil has 200 turns. So this is MP. And a secondary coil consisting of 3000 turns. So this is the number of turns on the secondary coil. So the secondary coil has 3000 turns. The primary coil is supplied with an effective AC potential difference of 90 volts. So this is the effective, or the voltage on the primary coil, in which is Vp. The voltage, or the potential difference on the primary coil, has the symbol Vp. What is the potential difference in the secondary circuit? So he wants me to find Vs. According to the equation, Vp over Vs equals to Np over Ns. And then you substitute. The primary voltage is 90, Vs is the unknown, equals Np, which is 200, divided by Ns, which is 3000. Now you can shift solve it on the calculator or rearrange. If you shift solve, you put fraction x equals fraction 200 over 3000, and then shift calc equal. So 1350. That means Vs was magnified to 1350 volts, was increased to this much. Or you can rearrange by cross-multiplying and then dividing by 200. So you'll multiply 90 times 3000 and divide it by 200. B. The current in the secondary circuit is 2 amperes. What is the current in the primary circuit? So he gave me the current in the secondary circuit to be 2 ampere. This is Is. He wants me to find the current in the primary circuit, so he wants me to find IP. Now remember, VS, IS, or IS, VS is the same thing, equals VP, IP. There's another equation in your book that says IP over IS equals to NS over NP. This also can be used to find the current, but we're just going to stick with this one since we have already found all its parameters. Secondary voltage, as we found, is 1350. The secondary current is 2. Primary voltage given in the question to be 90. And the unknown is the primary current. You can use the shift solve or divide by 90. So IP equals 2. Now we would expect that IP is less than 2. Let's see, 1350 times 2 divided by 90. That's going to give you a 30 amperes. Question 16, question 17, you can solve them by yourself. I'm going to put the solution in a moment.